Let's say you're given a 500 kVA transformer, and so we'll call it 500 kVA and 4.9% impedance. All right, and what you've got to do is the first thing you've got to do is you've got to find out what would be the full load current of that transformer. Well, you might remember from 2A this formula, P equals root 3 VL IL times the power factor. And also you might remember this, S equals root 3 VL IL. And of course there was Q in there as well that you might remember, but we're not going to worry too much about that. IL sine of the phase angle. We can pretty much leave that out for now. That comes from this triangle, your power triangle, if you remember. If that's a right angle, that's Q, that's P. Always the power is on the horizontal, and that's S. Yeah. All right. So what we're going to do is we're going to use the S formula, because transformers are always rated in VA, which is S. All right, and so we start here. We say full load current. We're going to access it using this formula, S equals root 3 VL IL, but we're only interested in L. We know VL. It's going to be it's a three-phase transformer, so it's 400 volts, and we know S, so I is the one we're looking for. So we're going to say IL equals, in our case, S is 500,000 over root 3 times 400. And of course, that's going to get us our full load current, and I would bang it in your calculator like this. If you got one of these buttons, you're halfway home. It's a great little button. It makes the fraction there so you can see it. 500,000 over root 3. Now we have to, if I just put root 3 times 400, you can see what we've done wrong here. The square root sign's gone the length of that, so we don't want that. We step away one and put times 400, and that will get us the answer we're looking for. So 721.68, so close enough to 722. Okay, so that's 722 amps. Well, that's the first thing that you got to find. But there's another step that's more useful. We want to know the prospective fault current of the transformer, and that's where your percent impedance comes in. And we can go back over our theory from 2A, but I'll leave that to you guys. I'm not going to do it here. What we need to be interested in is the prospective fault current at the transformer is just the full load current over percent Z. All right. If you want to look up and find out why, look up short circuit test. You would have done it in 2A, in G102. You'd have done it. No, you would have done it in 006, where you did AC machines. All right. So prospective fault current of the transformer is full load current 722 over percent Z. In this case, it's 0.049. And that ends up giving us, just bang that in, make a fraction again, 722 over 0.049, 14,734. If you're wondering where, we'll call it 735, 14,735 amps. That's our prospective fault current. That means that if you have a transformer like this, three phases, we'll always give you three-phase transformers. to puzzle out. All right, so this would be a transformer under normal conditions. Those three are phases, obviously, and that's your neutral. And of course, your neutral is always going to be Earth. So what we're looking at is for a prospective fault current is if you get a fault across three phases, which is a three-phase bolted fault. Three-phase bolted right at your transformer. We want to know how much current is going to be going through each of these windings. Well, we can look at them individually. This winding is shorted through there. This is all considered 0 ohms, and there's the loop for that winding. Here's the loop for this winding. Here's the loop for this winding. They're all the same. Okay, so we know that there's 230 volts across the winding because it's single phase and it's connected in star. 230 volts, and we know that 14,735 amps are going to flow. So it's just simple Ohm's law. So we can work out the impedance of the winding, which is important when you come this far. So impedance of the transformer is going to be equal to, again, it's just Ohm's law, V over I. So it's 230 over 14,735. Just bang that out in your calculator. That shouldn't be too difficult, I'm hoping. Where are we? 230 over 14,735. 0.0156 will do it. So, in that small amount of time, we've got prospective fault current at the transformer, and we've got the impedance of the transformer winding. That's going to be more important. That's going to be important later on.